Hey, good morning, everyone, and welcome to another session of our Sip and Ground Coffee, our morning web conferences. My name's Dan Painter, and I'll be hosting today's conference. By the way, just a shout out here, the thumbnail picture that you might see up on your screen, that guy's from Cushing and Sons, and they are a fantastic contractor up in the northeast part of the country. I think probably 90% of their installs are going to be Flint and Walling pumps, and I am aware that I think our marketing team was up there last week and was able to go out on some installations and just gather some good contractor information while they were up there. But anyway, good shout out to the thumbnail pictures. It's a heck of a lot better than mine. Today our topic is House of Resistance for subs. A few weeks back we did one for centrifugal pumps. And what the House of Resistance for subs is going to include today, it's a way of sizing up a submersible pump. Very simply, it's a way of sizing up a submersible pump, and it's gaining popularity for a couple of reasons. One, pump sizing. That's been a difficult thing for a lot of people to grasp and comprehend, and so therefore there was a lot of apprehension and just confusion and all that. So what we're going to do, and it was not an easy subject to teach either. So today we're going to talk about sizing submersible pumps, but we're going to use a totally different language. And this is called the House of Resistance for subs. Make sure I'm not forgetting anything up here before we get started. Okay, it looks good. All right, so here's how this works. And by the way, if this is your first time with us, welcome. And if you've been with us previous, welcome back. There's 5 things you need to know to select a submersible pump, all right? We're not looking for a whole laundry list of information. We're simply looking for 5 things to size a submersible pump. And here's what we need to know. First one up there in that little chimney is gallons per minute. That's going to be expressed as GPM. The second one is going to be the pressure. How much pressure do we want to operate the system at? We need to know that before we select a pump. The third one down there is what's referred to as pumping level. I'm going to circle back on all these as we go through them anyway, but pumping level would be the third one, followed by elevation. And the last one on that list is friction, sometimes referred to as friction loss. And basically what that does is that robs us of pressure. But again, I'm going to circle back on each of these rooms as we go through them. But those are the 5 things that you know, if you called me up next week or next month and wanted me to help you size a pump, those are the 5 questions I'm going to have. And the way that the House of Resistance works is pretty simple, because once we fill in those 5 blanks, we're now in a position to make a pump selection and size a pump. So let's look at the first one. All right, gallons per minute. Anytime we're looking at sizing a pump for gallons per minute, we want to look at what might be the maximum flow rate required. Now, a few weeks ago, we did sizing on surface pumps or above ground pumps, like your jet pumps, your centrifugals, and your self-primers. Centrifugals and self-primers almost always used for irrigation. Jet pumps almost always used for small to medium-sized houses. But when we get into submersible pumps, all right, we start looking at applications for submersible pumps, it's much, much broader. As you can see on your screen, submersibles can be used simply for a home water system, but they can also be used simply for an irrigation system. And there are many parts of the country, and any of you folks that are down in the southern part of the U.S., you know, Texas, Florida, a lot of those submersible pumps are going to have dual purpose. They're going to serve not only to bring water into the home, but also for the irrigation system. So that said, when we look at gallons per minute, we want to understand what is going to be the peak flow rate that will be required of that pump. And to determine that, we need to look at the applications. If this were just a home, water system, there's a very, very easy way of sizing up a submersible pump for a home water system. This method is referred to as the fixture count method. It's been around for decades. I don't know how well it's taught anymore, but it's a very, very easy way to come up with a means of determining how much water does a particular household need or require. And so the way the fixture count method works is very simple. We're going to total up the number of fixtures in a house, And whatever that total number ends up being, that should represent the gallon per minute rating of the pump. And by the way, as we go through today's presentation, if there's any questions that come up, and don't be bashful about asking them, but if there's any questions that come up, Renee will stop me and we'll take the question. We'll do our best at trying to get an answer for you, all right? So let's look at this little house we've got up here on the screen. Down in the bottom right, there's a kitchen down there, and in that kitchen, there's two fixtures. There's a sink and a dishwasher, all right? Just to the right of that, there's a laundry room. Now, in that laundry room, there's a clothes washer, and there's also like a service sink, like a laundry tub sink, and that's another couple fixtures, right? Upstairs, there's a full bath, and I think you can see where we're going. We're just simply counting up all the water fixtures inside this home. There's a tub shower up there, a lav, and a toilet. That's a full bath. That's going to be 3 fixtures. Downstairs is another half bath. So you've got another lav and a toilet in there. And then we also want to make sure we take into consideration any outside hose bibs, all right? So there's your fixtures. So in this case, we've got 1 outside hose bib. So when we total these all up, we come up with 10 total fixtures in that home. And again, the fixture count method would tell us that the gallon per minute rating of the pump should equal or greater, be equal to or greater than the total fixture count in the house. So that's a very easy way of determining how much water a particular home may need. Now, I'm not too concerned about ice makers and coffee makers and all this little piddly stuff that we can have in the home. What I am concerned about, though, is water using appliances like dishwashers and like clothes washers. All right, so we're going to move on. And again, if you've got questions, don't hesitate to ask. 10 gallon minute, that 10 gallon minute, then that's what we would put up there in that chimney, all right? That's what we'd put up there in the chimney. Now, if this were an irrigation system only, again, we're going to look for what we would determine to be the peak flow rate. And if you look at irrigation systems, it's not uncommon that they're going to be made up of multiple zones. And those zones can also have, different demands for water depending on what type of rotors or fixtures or sprinkling heads may be in that particular zone. But the whole notion here is as we look at these zones that are up here on the screen and we, want to determine which one of those is going to need the most amount of water, the greatest amount of water, it's that zone 4 up there. Those little circles with the black dots represent rotors, and if each of those rotors required a flow rate of 3 gallons per minute each, then you can see zone 4 up there, it's got 7 rotors. So it's going to want 21 gallon a minute when that zone comes on. And so you're going to need to size the pump for zone 4, because if you don't, and you size it for any of those other zones, when zone 4 comes on, it's going to starve for water, and you're not going to get the coverage that you're looking for. And so in this case, if it were irrigation only, I'm going to size this pump to whatever the zone that would have the greatest demand for water is going to be. What if it's both? What if we have to size a submersible pump for both the house and an irrigation system? And again, that's not uncommon in various parts of the country. Well, let's just look at this for a second. We have an irrigation system here. We just said a second ago that zone 4 was going to be the peak flow rate demand, and that was 21 gallon a minute. And if you recall, when we did the fixture count in the house, we came up with 10 fixtures, and so that was going to be 10 gallon a minute. And so I suppose if we're looking for a pump that's going to satisfy the peak flow rate of this system, which would include the house and the irrigation system, you're probably looking at something just above 30 gallons per minute, all right? 30 gallons per minute. And so if you go pick up a pump that's going to put that out, you're covered, right? You're very, very, very well covered. But I want to throw in just a little logic here, all right? Just a little logic. I want to put something up here on this screen. We need 31 gallon a minute to satisfy the peak flow rate. Now, when would that occur? Well, that would only occur at such time that zone 4 is up and running while they're taking showers and running dishwashers and flushing toilets inside the house, right? Probably not likely going to happen. not at the same time. So let's look at maybe 25 gallon a minute pump. And here's the reason why I'd go 25 gallon a minute or somewhere in that range. First of all, it will handle either peak flow rate. It'll handle the peak flow rate for the irrigation system, and it'll certainly handle the peak flow rate for the house. It just won't handle them at the same time, right? That's what we're talking about. But look at this screen. When zone 1's coming up and running, it requires what? It wants 9 gallon a minute. That leaves 16 gallon a minute left over for the house. Zone 2, that 18 gallon a minute, 7 gallon a minute left over for that. So you can see that as these zones go through, there's plenty of water left over for the house until you get to that zone 4, right? Once you get to that zone 4 there, that's the one that's going to, challenge us a little bit. I tell the homeowner, don't take a shower while zone 4 is up and running. What's zone 4 going to be up and running for what, 30 minutes, maybe 45 minutes? So I'm not going to go to the extent of a big 30 plus gallon per minute pump just because I've got one zone that's going to operate for a half hour. All right, I'm going to go with something a little more practical, more in that 25 gallon a minute range. But anyway, enough on gallons per minute. Where we're going with the gallons per minute is we always want to make sure that we select what we are going to be determining to be the peak flow rate for that pump. Right? So in this case of discussion today, I'm going to run with that 25 gallon a minute. I'm just going to go ahead and say, hey, yeah, we're going to size this pump up for both the house and the irrigation system. All right, so 25 gallon a minute, boom, right up there in that chimney. All right, let's move on. Let's go to pressure. I don't care what pressure we want to operate the pump at, but I do want to know what that pressure is going to be before I make a selection or size a pump. And in my opinion, or my experience at least, if you're sizing pumps just for irrigation only irrigation, most of those irrigation fixtures are going to operate just fine between a pressure of, say, 20 to 45 psi. There's a handful of them that want more pressure than that, but by and large, irrigation systems can operate at lower pressures than obviously a home water system. You have a home water system, I don't think you're going to have too many people happy with a 45 psi pressure. So in a home water system, we're going to be looking at 50, 60 or more pounds of pressure. So again, when selecting a pump, I want to make sure I pick the one that has the that's going to satisfy my highest demand for pressure.
Got a question here.
We got a question come in. All right, good. What's the question, Renee?
Can I save some money by putting in a smaller pump and just dealing with the lack of pressure?
Okay, there's a good question. Can I save some money by putting in a smaller pump and then just dealing with the lack of pressure? The answer is yes. Now, is that something we want to do? That's got a different answer, because you start putting in pumps that are undersized and they lack pressure, they lack flow rate. And if you're the installer or you're the contractor, I understand that there are people on budgets, but at the same time, if I'm the contractor and I'm going to be responsible and I need to stand behind this piece of equipment that I'm installing, I want to make sure I install what I believe to be the proper size. And anything short of that, there's going to have to be some contingencies here. And I'm not, as far as guarantees go and everything else. So not recommended to undersize pumps, really not, to save money. We'll talk about saving some money in a future web broadcast. We've got some good ways to do that. Anyway, to continue on, I'm going to go ahead and pick 50 psi. I could have picked 60 or 65. I could have picked 70. Whatever. But that pressure, in this case, I'm going to go ahead and drop that one in the pressure room. All right, so there we go. We got the gallon per minute filled out and the pressure room's filled out. Now we're going to go to this third one here called pumping level. All right. And this is where a lot of people, I think, probably fell overboard with confusion when it comes to pumping level. So a few things let's just talk about a well for just a few minutes here. And when we talk about wells, when they're drilled, all right, a driller will put some kind of a log together. And that log book can either be left with the homeowner, sometimes the contractor keeps it, sometimes they both have it. And sometimes we are able to find it, all right? If you are, it's a good thing, not a bad thing. But chances are you won't find it. But if you happen to find a well log, it's going to give you a lot of information with respect to that well. It's going to tell you what the diameter of the well is. It's going to tell you how deep it is. It's going to tell you where it's located, and it's also going to tell you what kind of geologic formations you had to go through, sand, shale, clay, granite, whatever that might be that you're drilling through to get to that aquifer, underground aquifer. It's also, and here's the nice one, it's going to tell you what that well will yield in gallons per minute. The rule of thumb, obviously, is that we would not want to put a pump in a well if the pump's gallon per minute pumping capacity is greater than that of the well yield, because you'll pump that well off very, very quickly without making some provisions for it, okay? But knowing what the well yield is would be a good piece of information. And then this last one up there, they talk about static water level, all right? I want everybody to understand what a static water level is. This is an easy thing to understand, all right? So basically what a static water level is going to be is you take the cap off the top of the well and you measure how far is it down to that water level in that well. How far down is it? And that's going to be measured and expressed in feet. And obviously static water level is going to be determined when the well is not disturbed, it's under non-pumping conditions, all right? So it's been sitting idle for a few hours. You go out there, you drop a measure down, and you determine how far down is it to that water level. This was an important thing to know back in the day, because the industry would say to us that if that distance is 25 feet or less, in other words, from the top of the well down to the water level, if that's 25 feet or less, the industry calls that a shallow well, all right? That's just an industry standard. Obviously, if it's more than that, more than 25 feet, the industry would refer to that as a deep well. When it comes to submersibles, I really don't care much about that, but this was a standard that still is in place today, and it was very important back in the days of jet pumps, because they made two types of jet pumps, right? They made a shallow well jet pump, and they made a deep well jet pump. But that's static water level, all right? Once you drop a submersible pump down in that well and you power that rascal up, more than likely that's probably going to pull that well down a little bit. That's referred to as drawdown, all right? That's referred to as drawdown. And it's at that point right there that pumping level would be determined, all right? I'm going to clean this up a little bit. I've done this so many times in front of so many contractors, and here's a situation, and I did want to spend a little time on this pumping level, but here's the situation. No one knows what that drawdown is unless you have a pump in there, right? Unless you have a pump in there. Well, if you got the old one yanked out, how do you know what that drawdown is going to be? Well, and again, when we talk about pumping level, that's typically the distance from the top of the well down to that water level while the pump's running. And again, now listen, if that well has a yield that's greater than the pumping rate of the pump, then you probably won't have any drawdown at all. But it's not uncommon to have some drawdown in a well. So therefore, when we determine the pumping level, where are you going to set that pump? It's obviously going to be below the static water level, right? It's going to be below the static water level. So if it's 20 feet below the static, or 30 feet, or if you want to just measure where the pump's going to be sitting at in that well, that's what we're going to use for pumping level, all right? That's because unless you can go out with a test pump, drop that down in a well and fire that thing up, and then determine where that drawdown is going to be in that well. And there's a few contractors that do that, but most don't do that, all right? So it becomes a bit of a guess. Choose where you set that pump, all right? So let's just suppose for example, we're going to set that pump at 58 feet. All right, so 58, it could be 158 feet, doesn't matter, but that's where I'm going to put in my pumping level room, all right, pumping level. All right, let's move to the third room, which is elevation. And by the way, that pumping level on a submersible pump, when we did the House of Resistance for centrifugal, that room was called lift. All right, centrifugal pumps have to lift water oftentimes before they can pump it. The submersible doesn't have to do that, right? It just pumps it. So elevation, all right? If this is a application where irrigation's involved and I've got terrain changes to overcome, all right, then in this case, I'm going to want to know what is the highest point in that irrigation system, right? So the point that I measured from the well down to the water level, I'm going to measure from that up to the highest point in that irrigation system. That's going to be, because when that pump's up and running and that irrigation system's also on, that pump's got to get the water all the way up there, right? So I need to know how far that's all part of the resistance this pump has to overcome. If it's just a home water system, I'm going to tell you what I do. I stop at the pressure tank. All right, I just stop at the pressure tank. So if this pressure tank was just a few feet above, where my well's located, that's where I'm going to stop. Now, I've had people tell me, "Oh, wait a minute, Painter, you showed a slide here a little while ago that showed a house that had a full bathroom in upstairs, and so why aren't you measuring all the way up to the upper floor to that bathroom?" And I'll answer that. And this is just an opinion, folks, so you do what you want to do. But I stop at the pressure tank because I've been in too many homes where they've got shower heads upstairs that look like manhole covers. I mean, I don't know what kind of water they're expecting to get out of there, but I know the plumbing leading up to it isn't adequate. And so I don't want to inherit that problem. I'll give them all the pressure they want at that pressure tank, all the pressure you want. But if you want to get that pressure upstairs, that's the homeowner's problem. I'm not going to inherit that problem. So let's just suppose that was 6 feet. All right, so boom, we're going to put 6 feet in the elevation room. We're almost done with this house. Again, the last one on here is friction, and anytime two surfaces pass by one another, there'll always be friction involved. All right, there'll always be friction involved. So when that pump pumps up, and it's pumping water through that piping, that water's rubbing along the inside walls of that pipe, and it's going to want to slow it down. It's the friction that's going to want to slow it down, and it ultimately will rob us of pressure. That's what it's going to do. All right. Now, the only way to determine how much friction are we going to incur or how much pressure are we going to lose is we need to use a friction loss chart. There's no other way that I can think of to determine that. And these friction loss charts, they're really a dime a dozen. They're in pump catalogs, they're in irrigation catalogs, they're in pipe catalogs. They're all over the place, and you can get them on the internet. So let's look at how to read a friction loss chart very quickly, okay? So there's these up on the screen are the 4 things we want to know to read a friction loss chart. We're obviously going to want to know a lot about the pipe. And so when it comes to that pipe, I want to know, how much of it do you got? How long is the pipe? What size is the pipe? And most importantly, what type is the pipe, all right? Because these friction loss charts are going to be specific to the type of pipe or the pipe type. I could put K copper up there if I wanted. There's all different kinds of types of pipe, but obviously water running through a stick of galvanized steel pipe is going to have a lot more friction loss as water running through a piece of smooth wall PVC pipe, right? They also want to know how much water you're going to run through that pipe. So let's just make some selections up here. Let's say we're going to have 250 feet of 1.25 inch, schedule 40, right? It could be any one of those combinations. The house doesn't care. Nor does the friction loss chart, all right? So we're just going to pick these 3 pieces of information. People ask me, how about T's and elbows? No, I don't worry about those. Well, wait a minute, Painter. We've always been taught that if you do friction loss, you need to consider T's and elbows. That's true. However, we're talking about sizing a pump today, and I'm trying to make this as simple as we can. And what you're going to find is that friction, even though that's part of the resistance this pump has to overcome, you're going to find that it tends to have the least amount of influence over which pump we're going to select ultimately. So in this case, I just want to know what size and how long is that pipe. I don't care about T's and elbows, but we do want to know how much water we're going to flow through it, and we determined that in the previous slide at 25 gallons a minute. So here are the information that we're going to go to this friction loss chart and make a determination, all right? So here we go. The very first thing you want to do when you pick a friction loss chart is make sure you got the right one, all right? So we're going to make sure we've got the friction loss chart that's specific to the pipe type, that's Schedule 40 PVC. We also said that we were going to use 1.25 inch, so let's put a mark around that 1.25 inch because just below that pipe type is the pipe size, all right? So we've got a inch and a quarter, and then over on the far left-hand column is your flow rate. So we had a flow rate of 25 gallon a minute, and we had friction or pipe size of inch and a quarter. So there's my mark around the inch and a quarter, and here's my mark around the 25 gallons per minute on that gallon per minute column. I come across from gallons per minute and down from the pipe size. I intersect in a box. It's not uncommon for friction loss charts to show the values two ways, and they're up on the screen right now. The first one is called velocity. I don't care too much about that one, but that's 5.47. What's that mean? Well, the velocity side of this means this. If you're going to flow 25 gallon a minute through inch and a quarter Schedule 40 PVC pipe, all right, you're going to flow 25 gallon a minute through that. That water is going to move at a speed or a velocity of 5.47 feet per second per 100 feet of pipe. Per 100 feet of pipe. That's always at the bottom of every friction loss chart, all right? Per 100 feet of pipe. Now, like I said, I don't care too much about that velocity side. What I am interested in is how much pressure am I going to lose, that pressure side. And what this is telling me is that if I'm going to flow 25 gallon a minute through Schedule 40 inch and a quarter pipe, I am going to lose approximately 3.5 pounds for every 100 feet of pipe. All right, so approximately 3.5 pounds. Well, how much pipe do I have? I got to move my head out of the way. I got 250 feet of pipe, all right? So what am I going to need to do? Well, I'm going to need to take that 3.5 times 2.5 to determine how much pressure am I going to lose in that 250 feet of pipe. And as you can see, the result of that math is 8.75. With the house of resistance, I always round. I never have anything on the right-hand side of a decimal point. So I'm just going to call that 9 PSI. All right, just going to round it up to 9 PSI, and boom. I'm going to put that up there in that friction loss room. We're done. We now have a house that's complete, and I mentioned early on that if we fill all those blanks in, we're now ready to go make a pump selection, right? Because in that house is all that resistance that pump's going to have to overcome. In order to get that flow rate, in this case, we want to get 25 gallon a minute to zone 4 and still satisfy that house. That's what we're talking about in this application here, all right? So what we're going to do is total up all those feet that are in that house. That's what we're going to do. And but when I look at the house, I got a little issue here, right? I got 2 of those rooms that are expressed in PSI, not feet. So I want to make sure all my rooms are in feet. And so to do that, all right, and this is a universal piece of information, I'm going to convert that pressure to feet, all right? So I got 50 PSI in the pressure room, 9 PSI in the friction room. I want to convert those over to feet. And here's how we do that. To convert those over to feet, you're going to take the pressure, whatever it is. It doesn't matter, whatever that pressure is, and you're going to multiply that out by 2.31, all right? 2.31. So let's do that. Let's take that 50 PSI that's over there in that pressure room. When we multiply that out times 2.31, you can see the result. Again, I don't use anything right-hand side of decimal points. 116 feet is my rounded number. Pop it in there and change that over to feet. Do the same thing with the pressure, or the pressure loss in the friction room, all right? I'm going to take that 9 PSI, which also is a rounded number, multiply that out times 2.31, and I'm going to round this number as well, coming up with about 21 feet, so there we go. That house now is in all feet. Sometimes I get asked, why 2.31, all right? So why 2.31? I'm going to answer that. First of all, I'm going to give you your code word for the day, all right? Your code word for the day is column. Column, like what we have on the screen. We take a 1-inch square column and set it on top of a table. So column is your code word. Email that in to marketing@flintandwalling.com, and you will receive your credit for today's session. All right, so back to this column. If we have a 1-inch square, which PSI is pounds per square inch, so if we have a 1-inch square column, sitting on the table. It's 3 feet tall. And I want to create 1 pound of pressure down at the bottom of that column, right? I want to create 1 pound of pressure. So now the question is, how much water am I going to have to pour into that 1 square inch column in order to create that 1 PSI down at the bottom? And therein lies the answer, 2.31 feet, right? So that's why it is what it is. It's 2.31 feet. Now, I hesitate bringing this up, but I will. If we wanted to go the other way, and I know a lot of the, well, not necessarily a lot, but in irrigation, I know there are times that irrigation contractors actually want to convert the feet to pressure, right, to PSI. So that multiplier is 0.433. So if you take that 116 feet up there in that pressure room, excuse me. Sorry about that. Remember that was a rounded number. But if I take that 116 feet times that 0.433, well, there it is. There's my 50 PSI coming right back at me again. So I guess if nothing else, it's a way of checking the math. But we now have this house all listed in feet. So we're just going to add these up. So when I add the pressure, friction, pumping level, and elevation, I'm coming up with just a little over 201 feet, all right? 201 feet. I hope that we haven't lost anybody in this explanation of the house of resistance, but it's these two numbers right there that the house got us to. And the house will always get us to these two numbers. It'll always get us to 2 numbers. Obviously, those numbers will change from one application to another, but let me tell you about those 2 numbers. This is what the pump industry is always referred to as total dynamic head, all right? This was the more traditional way of teaching pump sizing, but the language that was being used to do that was confusing too many people. It just was confusing way too many people. And so this is a different way to get there. So the feet that's in the house, that represents our resistance, all right? So total dynamic head, or TDH as the industry would call it. But let's look at how we're going to take these 2 numbers and size a pump, all right? So now we're down to gallons per minute and feet. Let's look at a pump curve. And let's look at how to read a pump curve. And then we finish that and we'll be pretty much done with this presentation, all right? When we look at a pump curve, all right, this is typical of a pump curve. And the first thing I want to do is get rid of all the stuff in the middle, all right? There you go. So you got 2 axes there. That's it. The one on the left-hand side is feet, and the one on the bottom is gallons per minute, all right? So you got feet running on the left-hand side, and you've got gallons per minute running across the bottom. So those are the 2 numbers that we're going to be looking for. When we look at pump curves, all right, just like friction loss charts were specific to certain pump or pipe types, pump curves are going to be specific to a series of pumps. If you look at the black dots that are out there on those pump curves, there's what, 5 of them up there? Those black dots, I guess sometimes we could refer to those as what we would call maybe the sweet spot, all right, the sweet spot on that curve. But if you come straight down from those black dots, and you hit that gallon per minute axis at the bottom, it's going to tell you what that particular curve is for. And so that first one there obviously would be for, well, I can't see it, 5 or 7 gallon minute pump. There's your 7 gallon, 10, so on and so forth, right? So if you come straight down from those sweet spots, you're going to know what that curve is for, whether it's a 10 gallon minute pump or a 19 gallon minute pump, whatever. The green shaded areas, all right? This is also kind of important to know about pump curves. You want to try to stay as close to that sweet spot as you can, all right? You want to try to stay as close to it as you can. It's not always possible to stay smack on it, but you want to try to stay close to it. If you happen to find yourself going left of that sweet spot, and we'll talk about this in our next, probably our next Sipping Ground Coffee web conference, we're going to talk about pump ends, all right? Pump ends. One of the reasons that Flint and Walling pumps do very, very well on that left-hand side of that curve, where that blue shaded area is, there's a lot of pumps out there, they won't give you any water at all. You get in that blue shaded area. But Flint and Walling has never destaged their submersible pumps. We have never done that. Our pumps have the same number of impellers in it they've always had. A half 10 gallon minute pump is going to have 8 impellers, 8 stages in there, all right? So, I mean, we've never destaged our pumps. But those companies that have, they're not gonna fare too well over there on that left-hand side of the curve, all right?
Got a question.
Got a question, go ahead.
Someone said, this is great. However, if I had a few moments with a customer, how could I summarize the importance of pump sizing so they're confident I'm not upselling them?
Okay, so I think if I understood that question correctly, Renee, the question was if, and I understand you don't get a lot of time with a customer as a contractor, especially. You don't get a lot of time with a contractor or with a customer, and I guess the way I would explain it is that when I'm going to size this pump up just so that whenever you would hit your peak demand, all right, that might be that might be Thanksgiving. That may be a halftime at a Super Bowl party, right? Whenever you may hit that peak demand, I'm going to have a pump in that well that's going to give you the pressure and the flow rate that you're going to need to satisfy that peak demand. And then I get to the end of this little presentation because I only have a few slides left. I also want to give you another sidebar answer to that question too, but I don't want to throw that in right now because I don't want to distract what we're doing here. But I will get back to that. And Renee, if I forget, bump me on that one. If you get too far on that left-hand side of that column, if you go way over there on that left-hand side, you want to avoid that, all right? Because you're going to overload the pump if you get over there, all right? So that's one part of a pump curve that you want to avoid. You also want to avoid the other side. If you get too far over on that right-hand side, over there you're going to overload the motor. So again, trying to stay close to those sweet spots. You're not going to be right on them, but within, and I'm going to show you a few here. Stay close to that as you can, all right? Let's just take this house that we had. We had 25 gallon a minute, 201 feet, all right? So we're going to go ahead and pull up a 27 gallon per minute pump curve. I'm going to pull up a pump curve that's kind of close to what my peak flow rate is going to be, all right? I don't want to look at a 7 gallon a minute pump when I'm trying to find a pump that's going to put out 25 gallon a minute. So here's the 27 gallon per minute pump curve, all right? First thing I'm going to do is I'm going to put a mark down there on that bottom axis, that gallon per minute axis. I'm going to put a mark at 25, right? Just kind of like what we did on the friction loss chart. I'm going to come up that side column where it says feet. I'm going to put a mark there at 201 feet. I'm going to come across and go up, and I intersect, right? I intersect. Everything below that red line that goes across that pump curve, everything below that is all that resistance that's in that house, right? It represents 201 feet. And when I look at what pumps are able to take care of the resistance, there's a lot of them. Look at that. There's, 4 or 5 of them that'll come up. They'll take care of all that resistance in the house. Now I need to find one that's also going to give me that flow rate. Well, that first one's not going to do it, right? If you come straight down from that first one, what's that going to give me? About 15 gallon a minute? That's not going to be adequate, right? That's not going to be adequate. Now, look at the far right-hand side, all right? Over there on that far right-hand side. Those are getting a little far away from those sweet spots. Plus, what are we looking at? 30, 35, 30? Way too much water. Don't need those. Those are not going to be good selections. So when I look at my pump curve here, I'm going to look at that, and this was by design. There's one that actually crosses right at that intersection, and that's going to give me everything I want, right? That pump right there is going to be a 1.5 horse, 27 gallon a minute submersible, but set at 201 feet, it's going to give me 25 gallon a minute. So it's going to take my resistance in the house and get rid of that. It's going to also satisfy my flow rate. There's the pump to sell. There is one just to the right of that. If you look over there, that one also could be used. That pump is a 2 horse, 27 gallon a minute, and it's going to get you a little closer to that 30, 31 gallon a minute that we were talking about earlier if you've got peak flow rate going on in the house and the irrigation system at the same time. But either one of those pumps would satisfy that application, all right? Let's just change this up a little bit. Let's say we had a house that had 25 gallon a minute, but this time our resistance inside there was 250 feet. So I've got a mark down there at 25. I need to move this one up to 250 feet. I'm going to come across there. Boom. Now, again, everything down below that red line is all that resistance. But there are pumps that'll also take care of that. There you go. There's 4 of them up there, right? And again, what you're going to be looking for is the pump that's closest to wherever you intersect with that gallon per minute and the feet line coming across, wherever you intersect. So that first one there, that's that's going to give me 20 gallon a minute. Now, here's a situation if you sell a smaller pump, in this particular application, everybody's going to be happy except zone 4. When zone 4 comes up and wants 25 gallon a minute, it isn't going to have 25 gallon. It's going to take everything that pump's got, which is still shortchanging it, and it leaves nothing for the house. So, shortchanging or downsizing a pump, not always the best thing to do. All right, so let's look. The next one over, there's the pump I'm going to select. That's right on, right? That's 25 gallon a minute. That is that 2 horsepower, 27 gallon a minute sub. But at 250 feet, that's going to give me 27 gallon a minute. I don't need 30 or 35 gallon a minute. So therein lies the way to select a pump right there. All right. One more time, let's change this up. I want to show you something here that I made a comment to you a few minutes ago, that when you do go to a pump performance curve, select a curve that is closest to the flow rate that you're wanting. Now, in this case, I've got a house that they want 15 gallon a minute, and I'm still using that 27 gallon a minute curve up there, all right? Let me show you why I don't want to do that. I want to get a curve that's closer to that 15 gallon a minute, and here's why. If I put a mark down there at 15 gallon a minute, all right, and I come and put a mark at 350 feet, and I come over and I come across. There we go. All right, now this is a 27 gallon per minute pump curve, and as we've talked about, look, there's 3 pumps that will take care of that resistance. Not one of them is anywhere remotely close to my intersection, but that one on the far left-hand side, that's not going to suffice. Whoops, that one on the far left-hand side is not going to suffice, because if you come, I got to get this back up here again. Sorry about this. There we go. I screwed up my slides there. Sorry about that. Here we go. There's no pump near that intersection, right? And you never would want to go to the left of your intersection, because there you're shortchanging your gallons per minute, right? When you come down, you're going to be short on gallons per minute. So you always want to go to the right. In this case, I'd have to go a heck of a long way to the right to get over to that pump that's real close to those black dots. If you follow that line, that's a 3 horsepower submersible pump putting out 25 gallon a minute. Well, good luck selling that 3 horsepower pump, right? Good luck. And that's what's going to happen if you don't use a curve close to what your gallon per minute rating is, right? So if we look at this one here, all right, this is a 19 gallon a minute pump curve. That's a lot closer than that 25, all right? And again, I determined that by running that line down through those sweet spots. Let's see what we've got going on here. 15 gallon a minute, put a mark there. 350 feet, put a mark there, and come across, go up, boom. There's several pumps that cross that intersection as well. There they are. And this is more the exception. This is more the rule rather than the exception. The first couple of performance curves I threw up there, I had a pump really close to my intersection. That was by design. This time, I'm out here in no man's land. I'm no man's land. And that happens a lot where my intersection's at. But if you look at your 4 choices, you got 4 choices there, right? That first one, that's not going to be good. That's less than 10 gallon a minute. The second one over, that's just to the right of my intersection. That looks like a good pump to choose. That pump's going to give me, little more than the 15 gallon a minute I'm looking for. But those 2 pumps over on that far right-hand side, obviously, that's more pump than I need. So you can see the one closest to my intersection right there is the one I'm going to choose. It's going to give me 25 gallon a minute. It's going to give me 17 gallon a minute at 350 feet, but it satisfies the house. It satisfies the gallons per minute. That's the pump I would put in there, a 2-horse 19. There you got it, sizing up pumps. I've got a couple of announcements here to make before we, by the way, when we did the House of Resistance for centrifugals, there's a workbook And then there's a worksheet that accompanies that presentation. And it allows you to just do some, this is laminated, so with a dry erase marker, you can size pumps all day long on this. If you are interested in the same type of documents for this House of Resistance for subs, please email the marketing department. That'll create a demand. And I'll tell you, once a demand's created here at Flint and Walling, people listen. So do that, and we'll probably get that document coming out real quick. Make sure you remember that code word column. In some upcoming sessions, we are going to be talking about our brand new Commander 2 and 3 variable frequency drives. These things have gotten legs underneath them and really become popular. Check with your sales guys, your sales teams. We're going to be talking about this in the next couple of weeks or so. But make sure you get a hold of your sales guys with this. This is a very affordable variable frequency drive that really can address all applications: single phase, 3-phase, 2-wire, 3-wire, 115 volt, 230 volt, so on and so forth. Anyway, that's up and coming shortly. Make sure you subscribe to our YouTube channel and follow us on any of those social media platforms. Any other questions coming in, Renee?
Yep.
All right.
Someone asked, if a customer plans to install a robust system and a water softener, does that factor into sizing?
So so I guess I'm going to paraphrase that. If a water softener is also used in a home, and we could include filters with that as well, would I consider that as an appliance like I did the dishwasher or the clothes washer? Probably not. And I want to give you the reason why. Okay, first of all, a water softener, when it actually uses water, when it goes through its cleaning process, that's typically in the middle of the night, 2, 3 o'clock in the morning, maybe 1 o'clock in the morning. Who's using water at that time? Nobody. And so, there's usually plenty of water left over for that to regenerate itself with. Other than that, water's just simply flowing through it. It's not actually using up water like a dishwasher with the, where it's got the rinse cycle and the wash cycle. Same with the clothes washer, where it's dumping water down a drain. The only time a water softener does that is when it regenerates at 2 o'clock in the morning, and that probably is every other day, maybe every third day, maybe once a week. I wouldn't take that into consideration, no. Sorry about that long-winded answer. Any more out there? Questions?
Yeah. So if I were to size a pump on, say I'm getting a new house and I want to eventually upgrade and get a pool or, add something else to that, is it better to size your pump for something larger to future-proof yourself, or should you just kind of wait until you have it?
Well, that is also a good question. That's something I think I would ask if I were a contractor. I'd ask my customer, is there interest or is there plans for, expanding, which might increase your demand for water? And when is that going to happen? If that's something that's going to happen in the near future, I might want to go ahead and size a pump today to accommodate that. Like I said, there was a pump we sized a few minutes ago that gave you more water than you actually needed. But those type of pumps can take into consideration future expansion. That really comes into play with irrigation. A swimming pool, you're going to fill it up once and then you're going to be topping it off periodically. Not a lot of water used there. But irrigation, if you're going to expand on that, yeah, you would want to consider a pump that could handle both the house and irrigation. All right? Anything else? Have I left anything out today? I'm trying to look at these notes that come up. All right, so email your code word in column, and I guess with that, we'll knock this off and call it a day. Call it a morning. Thank you, everyone. Talk to you soon. Take care. Be safe.